Hello, welcome to my video series of data structures. This is part 1 of module 6, the heap data structure. In this video, we will motivate the heap data structure and introduce its fundamentals. Imagine you want to spend your free time playing video games. As a new gamer, you are unsure about which games to try first. To simplify your decision, you decide to base your choices on game ratings. Your selection process is straightforward. You will always choose the game with the highest rating available at the time. Keep in mind that completing a game takes some time. During that period, new games might be released, and they should be added to the candidate list for future selections. Once you finish a game, you will remove it from your list of candidates to ensure that you don't play the same game twice. In this case, you need a data structure to manage a dynamic set of candidate games. The data structure must support both insertion and deletion, as new games need to be added to the list and completed games need to be removed. Additionally, the data structure should efficiently identify the game with the highest rating at any given time. To meet these requirements, we define 4 fundamental operations required by the data structure. First, the construction operation initializes the data structure using a set of unsorted games and their ratings. Second, the find best operation retrieves the game with the highest rating from the candidate list. Third, the insert operation adds a newly published game along with its rating to the candidate list. Fourth, the delete best operation removes a completed game from the candidate list. It assumes that the location or reference of the game to be deleted is known, as the information would have been obtained from the find best operation. These operations can be implemented using 4 data structures we have discussed: the unsorted array, the unsorted linked list, the sorted array, and the sorted linked list. We will analyze the time complexities of the construction, find best, insert, and delete best operations for each of these data structures. We will also compare them with the time complexities of those operations when using the heap data structure. This will highlight the advantages of using a heap for handling similar situations. Finally, we will introduce the fundamentals of the heap data structure, covering its key properties and basic implementation. First, we use an unsorted array to store the set of n candidate games. Since the games do not need to be sorted by their ratings, we can load them directly into the array in O(n) time. For example, the array shown here stores a set of games along with their ratings. The games are not sorted by their ratings, and their orders are arbitrary. To find the best game, we must examine each game in the array, as the games are unsorted. This requires O(n) time. Inserting a new game is straightforward, as we can append it to the end of the array without maintaining any order. In our example here, we can directly append the game Final Fantasy to the end of the array. This operation takes O(1) time. Finally, to delete the best game, we can override it with the last game in the array, again because we don't need to maintain any order of the games. Here, we can remove the game Black Myth with Final Fantasy, which implicitly removes Black Myth from the list. This operation also requires O(1) time. In summary, with an unsorted array, the construction and find best operations each require O(n) time, while the insert and delete best operations can be performed in O(1) time. Second, we use an unsorted linked list to implement these operations. For construction, we can directly load the data into the linked list without sorting them, which takes O(n) time. For find best, we need to traverse the entire linked list to examine each node and find the best game. This requires O(n) time. For insertion, we can attach the new game to the tail of the linked list. This operation takes O(1) time. Finally, for delete best, if the address of the game to be deleted is known, the node can be removed with a fixed number of pointer adjustments. This operation also takes O(1) time. Overall, using an unsorted linked list results in the same time complexity for the operations as those for an unsorted array. The construction and find best operations each require O(n) time, while the insert and delete operations can be performed in O(1) time. Third, let's consider using a sorted array. To construct a sorted array, we must first sort the games based on their ratings, which takes O(n) log n time. Note that in the array shown here, all games are now sorted by their ratings. Once the games are sorted, finding the best game simply involves returning the first game in the array. This operation requires O(1) time. If we need to insert a new game into the sorted array, we must first identify the correct location for insertion. This can be done using binary search, which requires O log n time. After identifying the insertion location, we need to shift all games after the location to make space for the new game. For example, when inserting Final Fantasy, we will shift Diablo, FIFA, and Tomb Raider one position each to create an empty slot for the new entry. In the worst case, we may need to shift up to O(n) elements, making the overall time complexity for the insertion operation O(n). To delete the best element, since it is always located at the starting index of the array, we simply update the starting index to point to the next element. For example, if we want to delete Black Myth from the array, we update the starting index of the array from 0 to 1, making Super Mario the first game in the sorted list. In summary, with a sorted array, the construction operation requires O(n) log n time. The insert operation requires O(n) time. The find best and delete best operations can be performed in O(1) time. Finally, let's consider using a sorted linked list. To construct the linked list, we first need to sort the games, which requires O(n) log n time. The best game is always located at the head of the linked list, so finding it requires only O(1) time. To insert a new game, we first spend O(n) time to examine each node in the list and identify the insertion point. Then, the insertion can be done using a fixed number of pointer updates. Overall, the insertion operation requires O(n) time. Finally, to delete the best game given its location, we only need to update a constant number of pointers, which requires O(1) time. Overall, the time complexities of the operations implemented using a sorted linked list are identical to those achieved with a sorted array. The construction operation requires O(n) log n time, the insert operation requires O(n) time, and both the find best and delete best operations can be performed in O1 time. Compared to arrays and linked lists, the heap data structure offers different time complexities for these four operations. Specifically, when implemented with a heap, the construction operation requires O(n) time, the find best operation requires O1 time, while both the insert and delete best operations take O log n time. The primary advantage of the heap is that none of the find best, insert, or delete operations require O(n) time. In contrast, at least one operation in array or linked list implementations has a time complexity of O(n). This efficiency is due to the unique structure of a heap, which partially sorts the data elements to obtain a more balanced cost across these operations. Note that in real-world scenarios, these find best, insert, and delete best operations are typically executed as a sequence in random order. As a result, the running time of a sequence of these operations is dominated by the slowest among them. For array and linked list, the slowest operation runs in O(n) time, whereas for a heap, the slowest operation runs in O log n time. Note that the construction operation is only performed once throughout the entire life cycle of the data structures. Hence, its efficiency is less important compared to the other find best, insert, and delete best operations. Nevertheless, heap still offers the best time complexity O(n) among all the other competitors. Now, let's explore the details of the heap data structure. Conceptually, a heap is a complete binary tree that satisfies the heap property. A complete tree is a tree in which all levels, except possibly the last, are fully populated with nodes. On the last level, nodes are filled from left to right without any gaps. A binary tree ensures that each node has at most two children. For example, the tree shown on the left is not a complete binary tree, because there exist gaps at the first and third positions of the third level. In contrast, the tree shown on the right is a complete binary tree, as all nodes adhere to the structural requirements. The heap property varies depending on the type of the heaps. One type is the max heap, which is designed to efficiently identify the largest element in the set. In our example where the goal is to find the highest rated game, a max heap would be appropriate. Conversely, a min heap is used when the task is to find the smallest element in the set. In a max heap, the heap property ensures that every node in the tree is greater than or equal to its children. As a result, the largest element is always located at the root of the tree. In a min heap, the heap property states that every node must be smaller than or equal to its children. Consequently, the smallest element is located at the root. Here, we show an example of a max heap. In each tree node, we store a data element, which includes the name of the game and its rating. Its structure is a complete binary tree, and the rating of each node is greater than or equal to that of its two children. For example, node A has a rating of 9.8, which is greater than the ratings of its two children, 9.5 for node B and 9.3 for node C. Note that the heap does not impose any order on sibling nodes. This means that the left child of a node could be smaller, equal to, or greater than the right child. For instance, node D's rating, 9, is greater than the right sibling node Yi's rating, which is 8.5. On the other hand, node F's rating, 8, is smaller than its right sibling node G's rating, which is 9. The tree shown here is a mean heap. Each node stores a game and its price. In this mean heap, the price of each node is lower than or equal to that of its children. Note that the heap property organizes the data elements at different levels based on their values, but it does not guarantee any order between siblings. This is why we say that the heap partially sorts its data elements, which distinguishes heap from other data structures. The heap property also ensures that the smallest or the largest element is always located at the root. This makes the find best operation highly efficient, with a time complexity of 0.1. After understanding its theoretical structure, let's discuss the implementation of a heap. Although the heap is conceptually presented as a tree, it is actually implemented using an array. This is possible because the heap is a complete tree. In this implementation, the array represents the level order traversal of the tree. This means that the tree is traversed level by level from left to right, and the values are stored in the array in the same order. For example, here we show the tree representation of a heap on the left and the array representation of the heap on the right. In the array representation, the first column corresponds to the indexes of the array, and the second column stores the content of the data elements. The first position of the array stores information contained in the root node A. The second position stores information contained in the left child of A, that is, B. The third position stores information contained in the right child of A, that is, node C, and so on. Beginning storing the data elements at the first position of the array makes the mapping between the tree nodes and their indexes easier, which we will see in a minute. In this implementation, the root of the heap is stored at the first position of the array. The left children of each node are stored at the even indexed positions of the array, while the right children are stored at the odd indexed positions. For example, the left children, nodes B, D, and F, are stored at array indexes 2, 4, and 6, respectively. The right children, nodes C, E, and G, are stored at array positions 3, 5, and 7, respectively. Given a node stored at the ith position of the array, say AI, we can determine the indexes of neighboring nodes as follows. First, the index of the parent of AI is given by the floor of I over 2. For example, node B is stored at index 2. Hence, its parent should be stored at index the floor of I over 2, which is 1. Indeed, the parent of node B, node A, is stored at index 1. The left child of AI is stored at A2I, and the right child of AI is stored at A2I plus 1. Observe that for node B at index 2, its children should be stored at A4 and A5. And we can verify that node B's children, node D and node E, are indeed stored at those positions. Finally, if I is even, AI is the left child, and its sibling is AI plus 1. If I is odd, AI is a right child, and its sibling is AI minus 1. The mapping between the tree nodes and array indexes allows constant time access a node's parent, children, and sibling. This efficiency is crucial for the efficient implementation of heap operations. While it is possible to implement heap using a tree data structure, the array implementation offers two advantages. First, in an array, all data elements are stored in consecutive memory blocks. This improves cache performance and makes data access more efficient. Second, the array implementation does not require pointers to link nodes, saving memory space compared to the tree-based implementation. Finally, note that the behavior of a heap is similar to that of a queue, as both maintain a dynamic set of data and are designed to pop elements. However, they differ in that a queue always removes the element that was inserted first, while a heap removes the best element, as determined by a specific comparable measure. This measure, such as the game rating used to decide which game to play first, is referred to as the priority of data elements. For this reason, the heap data structure is also called the priority queue. These terms, heap and priority queue, can be used interchangeably. In summary, we introduced the heap data structure, which enables efficient identification of the best data element in a dynamic set. Conceptually, the heap is a complete binary tree that satisfies the heap property. While it is conceived as a tree, it is typically implemented using an array, offering more efficient data access and space utilization. Thanks to the heap property, the best element is always located at the root and can be retrieved in O1 time. In the next video, we will dive deeper into the details of the insert, delete best, and construct operations, along with analysis of their time complexities. Thank you for watching, and see you next time.